what this boils down to is that really there are only 5 allowed combinations between the atomic orbitals on 2 fluorine atoms. And they're listed for you here. The 2s with itself on the other atom, the 2s with the 2px, which is aligned with the internuclear axis, so we're allowed to make that combination, and then the homo-orbital combinations between the p orbitals, so the px with itself, the py with itself, and the pz with itself are all allowed. But there's a little problem here. So remember I said before, 8 atomic orbitals in means 8 molecular orbitals out. But we've listed 10 combinations here. So the constructive and destructive combinations are listed here. Hence the plus minus in each of these cases. So there are 10 combinations represented here, but we only have 8 molecular orbitals that we can possibly produce. So one of these sets of combinations, or 2 total, right, has to be something that we can't consider. We have to throw out 2 of the allowed combinations. The way we decide which combination to throw out boils down to the energetics of the combination. So remember, I talked about in the past 3 different key concepts to deal with when combining orbitals: distance, symmetry, and energy. Distance, since we're dealing with the diatomic and we have the freedom to move the atoms wherever we want to, is not a concern. We imagine the atoms being at their optimal distance when we start. We took symmetry into account when we looked at the allowed and disallowed combinations. All of these combinations listed here are in fact symmetry allowed. What we haven't considered yet is the energetics of the combination. And when it comes to energy, what you should keep in mind is that orbitals that are similar in energy will overlap more efficiently than orbitals that are not similar in energy. So for instance, the 2p orbitals interacting with themselves are all going to be great combinations because those orbitals are equal in energy, and so there will be a large stabilization of the bonding orbital when those orbitals interact. Similarly, the 2s with itself will be a favorable combination because those 2 orbitals being equal in energy will lead to a large stabilization of the bonding orbital. The anti-bonding orbital that results is highly destabilized, but since we probably won't fill that orbital with electrons, we don't have to worry about that combination. Hopefully what you've noticed by now is that it's the combination between the 2 orbitals of different energy that we throw out. So the 2s plus the 2px and the 2s minus the 2px. Both of those combinations involve orbitals of substantially different energy, and so those will be disfavored combinations relative to the ones in which the orbitals are equal in energy. We do still see combinations of orbitals that are different in energy, don't let this mislead you, but in the case when we need to throw out an interaction, we can look for interactions between orbitals of different energy and instantly throw those out. And that's where we get the motivation to throw out the 2s plus or minus 2px combinations because they're energy inefficient. Alright, now let's move on to actually building the combinations. So when we combine the 2s with the 2s, we can do so in either a constructive or destructive manner. If we do so in a constructive manner, we generate an orbital that just kind of looks like a blob between the 2 fluorine atoms. Say we brought in a 2s of white phase and another 2s of white phase. That leads to an orbital with just all the same phase between the 2 nuclei, and this is clearly a bonding orbital because there's a lot of electron density between the nuclei there. The sigma star, on the other hand, we bring in orbitals of opposite phase. So say this is the 2s plus the 2s. 2s minus the 2s would look like this. And we call this a sigma star type combination because it's definitely anti-bonding. You can see between the 2 nuclei we have a node, and this is again the 2s minus the 2s combination, and it's sigma star. Now let's look at the 2p sigma combination. So notice the 2 fluorines do have 2p orbitals, that are pointing directly at one another, and that's the px combination, right? So 2px plus 2px is actually a sigma combination. So to draw directly on the Lewis structure, you can imagine the orbitals overlapping like so on fluorine. And clearly that's a sigma type interaction, and the one I've drawn there is the constructive. So take that combination and sort of combining the orbitals together, the resulting MO would look something like this. On the other hand, if the phases were opposite, so the combination in which we're bringing two orbitals of opposite, or two lobes, I should say, of opposite phase together, we get something that looks quite a bit different. That's definitely an anti-bonding orbital. So taking 2p minus 2p, we would have an orbital that looked like so. And notice this is, again, decidedly an anti-bonding combination because of that node between the nuclei there. This orbital has substantial electron density between the nuclei, so this is a bonding orbital. This one an anti-bonding, and that's where the asterisk comes from right there. Finally, now let's look at the pi-type combinations. And I've introduced 4 new orbitals here because there are 2 sets of pi-type combinations. Both the py with itself and the pz with itself are examples of pi-type combinations. And to see this, remember that the x-axis is the internuclear axis, the y and z-axis are perpendicular to it. So as we bring the atoms together along the x-axis, the 2 y-axes are aligned parallel, as are the 2 z-axes. As a result, we'll see pi-type overlap between those p orbitals. And just to explicitly draw out an example of that, let's look at the pz's. So we're bringing the 2 orbitals together, like so, with the same phase, and so the resulting MO will look like this, kind of a blob above and a blob below the internuclear axis. And of course those will have opposite phase, and so we do see a node, you'll notice, in the pi-type combinations. For the pi star, similar idea, except the 2p minus the 2p. That gets us to an MO that looks similar to the starting atomic orbitals, just with an extra node between the nuclei, like so. So we still have that nodal plane along the internuclear axis, but we also have another one between the nuclei, and that shows you that this is clearly an anti-bonding orbital, whereas this one is bonding. Notice that the energies of the pi and the pi star aren't quite as extreme as the sigma energies, because pi-type overlap is less efficient than sigma-type overlap, and so that less efficient overlap leads to less stabilization and less destabilization for the bonding and anti-bonding orbitals, respectively.